So it was a great honor to be elected to give this prestigious lecture by the AHS, because when you look back at the names of the people who had given it in the past, you find out that all the great leaders of our rotorcraft community were involved in that. But today I'm going to drift back a little bit, and I'm going to talk to you maybe not so much in technical terms, but more in terms of what it's like to actually be an engineer who actually has a job. His job is to try to design a helicopter or a tilt rotor that had a certain mission requirement. And I want to approach that from the position of speed, range, performance, hover capability, and things like that that the aerodynamicist must deal with in life. And so from that perspective, we use a lot of analytical tools. Many of the analytical tools we get from places like the universities or from NASA or from the Army. And then some of them we have to make internally to Bell. But when I start giving this lecture today, you have to recognize that I got to work with a lot of very intelligent individuals and engineers over my career. And so some of the stuff that I'm going to report on today, they had a large part in that contribution. So in honoring these individuals, at the bottom of each slide, you will see a reference that reported on this work, because I think it's important to recognize these individuals. I gathered a lot of material for this report, but unfortunately it has to fit within a 1 hour time frame, so a lot of stuff was on the cutting floor. But some of that will be in the paper. So basically I'm going to take some snapshots in time on how you really went about calculating. But first I want to talk about who we're honoring here. Professor Nikolsky was a pioneer. I had the privilege of working for Bob Lynn, who was our Executive Vice President of Engineering, who actually was a student of Professor Nikolsky. And I want you to read this thing. I won't read it to you because I know you can read. I don't like presentations where they read slides to you. So the main thing out of this was he learned very quickly you need to have fundamental understanding supported by test data, and then you can believe your analysis. So the question is how has that fared over the years? Because one thing we wanted to do was constantly improve our analysis. And just for the future, one of you individuals sitting out here today may be giving this lecture in the future. And if you ever want to know who Professor Nikolsky is, you can go to Bob Lynn's 1992 Nikolsky lecture, and there's Appendix A in there that completely talks about Professor Nikolsky. Anyway, let's get started. There are two slides up here. When I first joined the company, we were dealing with a lot of tail rotor problems. And so the side here you can see the tail fin actually takes away thrust from the tail rotor. So we had to learn how do we do the fin blockage. So we ran a little experiment. S over A is basically the area that the tail rotor blocked, the disc area blocked. And you see we tried to, and we saw that a tractor tail rotor, when you think of tractor, it's on this side of the fin. When you think of pusher, it's pushing the back end. So either I'm pulling the back end or I'm pushing the back end. And so there are different losses associated with that, with the tractor having the greatest penalty, the pusher having the lesser penalty. However, we made a mistake. At the time, we didn't know we made a mistake, of course. But what we did, when you look at the tail rotor, if this is a vertical fin, we always have a sign convention. Which way is the top blade going? Is the top blade going forward, or is the top blade going aft? So it depends on which way you orient the tail rotor. So unfortunately, we made it so the top blade was going forward. We thought that was really cool. We'd couple up with the dynamic pressure from the main rotor. It'd be great. However, when we were in Vietnam, we quickly learned that when we had a tailwind, we had a real problem. We had a control problem. And we lost a lot of tail rotor thrust. And so finally, we began to understand that the ground vortex that's formed on an aircraft when you're in rearward flight can actually subtract from the dynamic pressure of the tail rotor. So we're in a pickle. We need a design change quick. So being innovative, what someone thought of, and it wasn't me, that what we would do, we would simply flip the tail rotor from the pusher side to the tail rotor side. That had two advantages. I got a top blade going aft the tail rotor, and I didn't have to change the gearbox. So we were able, just by simply moving it over flipping it over, we were able to solve that problem. Of course, we learned a valuable lesson at that point in time, and that's from then on, tail rotors should have top blade going aft. Today, you wouldn't think anything about it because you look in the literature and see that. Another real important component of helicopter performance is what is the drag of the fuselage, what's the drag of the hub, what's the overall drag of the aircraft. Wiesner and Keyes did a really interesting paper in the early 70s where they show the components of the helicopter parasite drag. And so when you look at this, you can see the big offenders, the landing gear, okay, because back in the day we didn't retract it or we had skid gear. The basic fuselage, main rotor hub, nacelles, tails, tail rotor hub, and protuberances and momentum losses. Now in this particular thing, the red is the current status of where we were in 1970. The blue is where they had hoped we could actually get to. Now, call your attention, landing gear, okay, we suck up the gear today, we sort of work on that, but you still have a pylon of some kind unless you can make it go in your fuselage. So that piece has been worked on. I want you to look at the main rotor hub because through history of the next few years, I'm going to show you that tail rotor hub, the main rotor hub keeps coming up as people looking at it. And so the interesting part, well, what is that drag? You can see that drag is a big player in the parasite drag of a helicopter. So I'm going to look at some of the early stuff that we did. Bell in the 60s, we were trying to find out how to get a helicopter to really go fast. We took the conventional two-bladed rotor in the upper left-hand slide, and we tried different things. We put a pylon that would cover up the rotating controls. We put fairings around the cuff. We even put this giant ellipsoid on there. And you can see in the lower right-hand side the effect. We made about 1.5 foot gain out of that. However, you put all that stuff up there, the pilot can no longer see the rotating controls. He can no longer check out and see if there's any interferences or anything. As a result of that, they never made it on an airplane, never went into production. So that information was out there. If you go to the mid-70s, Tom Sheehy from Sikorsky Airplane did an in-depth study of what it takes to find out what hub drag, what really affects hub drag. On the left, you can see the hub frontal area versus the incremental drag. And what he determined from that basically was that if you could take the profile area, that you could pretty much estimate it. However, there was a big controversy about, did I need to rotate the hub in the wind tunnel test, or can I just do it statically and index the hub? So we can see here that when he looked at it, there was a variable answer there. He wasn't sure what to say about that. So at the point, he sort of concluded that hub drag may not be affected by rotation. Because if you rotate, of course, you have a more complicated test that you have to go run. So we sort of talked about the hub. So how do we do this? We always had these small scale tests, you know, depending on where you test. If you're in a 7x10, it's usually a 5th scale model. And so let's look at some small scale stuff. So Bell, we had the Model 222. I must confess we did not quite make the performance in forward flight that we were supposed to make. So our leadership decided that we should take a real aircraft, which is shown on the right, that's a real flying prototype, take it to the 40x80 wind tunnel and run a test and see if we could understand why we weren't really making our performance. Meanwhile, we took a 5th scale test that we had earlier. Well, we had really disappointing results out of that test in that the 5th scale wind tunnel test data did not match the full scale wind tunnel test. But in talking with everybody, we said, well, the real problem was, and this was not on the left-hand side, that's not actually the mounting system that we used for the first test. So we came back and we asked ourselves a question, what could be wrong? Well, anybody that does force and moment tests knows about tears and interferences. You have to do the image, you got to flip it upside down and get your model data. So we went back to the LTV wind tunnel, 7x10, and we actually built exactly the same mounting system that was actually used in the 40x80 wind tunnel. And we did T&Is on that test, and we flipped it upside down. Once we did that, we correlated very closely with the wind tunnel data between the small scale and the large scale wind tunnel. So the lesson learned here is you really got to do T&Is, and you really got to pay attention to how that thing is mounted in the wind tunnel, even if you're in the 40x80. So we talked a lot about drag and determining that. Now let's talk a little bit about performance. In the late 60s and early 70s, the only performance data we really had was momentum theory, Gasol and Meyer type approach. And we used to have some factors that we would apply to the induced power and things of that nature. So we got to looking at two places. And two places that you really are interested in calculating the performance on is the minimum power. And the minimum power is in the speed power bucket where the power is minimum. And that has two significance. One, that's where you do all your rate of climb testing to see how fast you can climb. And the second thing, if you happen to be a twin-engine aircraft, that's how you determine what your single-engine stay-up capability is. So it's really important because remember early on you promised somebody this airplane could stay up single-engine to 4,000 feet on a standard day. So if you miss that power, you really can be in trouble. So we went and looked at a bunch of things. We put some trim models in our code, but it was still momentum theory. As you can see in the minimum power thing, we were maybe close to 3 to 5% problem. In the forward flight thing, we were very optimistic by 6%, basically. And so this was still a big problem for us. And so we really wanted to continue to understand what do we need to change in the methodology for the forward flight. However, before I go there, I want to talk a little bit about hover data. Remember, our early hover models were simply momentum theory. The thing you have to realize about momentum theory is that it captures the fundamentals of the flow really good, but it gives you no details of the flow. So you can sort of have a stream tube, you can know how much momentum passed through it, but you don't know how it's distributed inside that stream tube from momentum theory. So Landgrebe at Sikorsky, Tangler at Bell, and Kasurik at Bell spent a lot of time and visualized, took a lot of type of slurring and other flow pictures, and we began to see how the rotor wake actually contracts and then how it diffuses again. And so this was what we began to develop this based on the aspect ratio of the blades, number of blades, and different parameters to try to see if we could come up with a prescribed wake. And a prescribed wake means you tell it what it looks like, but you do calculate a wake. You just position it, and thereby you get the correct inflow angle at the rotor blade itself and hover. At that time, it was sort of expensive to run this, so we tried to get workarounds. But anyway, we went to work on it, and we did that, and we can see that we thought that we could pretty much get our hover methodology to give us the actual altitude at a given gross weight that I could actually lift in flight test within about plus or minus 3%, which was fairly decent at that time. One thing that Kasurik found, since I was always in handling qualities early in my career and I designed tail rotors, was that a main rotor is like probably 16 to 17 aspect ratio. A tail rotor is an aspect ratio of 5 to 6. So when you design it, so you could get the thrust and power right, you could figure that out, but could you figure out the blade angle? And what Kasurik's code did that our momentum code could never do was Kasurik's code changed the lift curve slope properly that we could actually calculate the required blade angle now to go sideward flight correctly. So aspect ratio is a big deal when you're doing tail rotors, and you need to make sure that you understand that particular issue when you go to calculate the blade angle. Because remember, you design a rotor hub, the blade fits in the hub, whatever you design in, that's all you get at the end of the day. You don't get to throw it away, go get buy a new hub. Program managers get real upset about that if you tell them that. So now I'm going to switch to a subject that's a little different because there are usually very many static tests you can run, very many qualification tests that we ran on aircraft, and there are many pieces to go into aircraft design, into actually flying the airplane. However, sometimes you really have to go into the dynamic environment. And we're going to talk a little bit about something I had to do in the dynamic environment. So in the mid-'80s, we started getting a lot of reports and reading in the media about something called tail rotor stall and tail rotor breakaway. And there are a lot of situations where there were certain situations where they believed the tail rotor was actually stalling on them. And some people actually thought the tail rotor quit producing thrust when it stalled. And so there was a lot of stuff came out. So suddenly the Army changed the emergency procedure that said if you start spinning to the right out of control, you should reduce your collective pitch, which will reduce the torque. You reduce left pedal, which meant I want to spin faster to the right. I never could understand that one. And then you apply forward cycle to try to fly out of it. And the thing that bothered us a lot was that we had fully qualified this airplane. We knew we had enough control power on the tail rotor. We hadn't experienced any tail rotor stall. So we couldn't understand exactly what was going on. There were several accidents that were really bothersome to us, and that was if you're at an airspeed between 15 and 20 knots, and you were making right hovering turns, that people seemed to lose control of their airplane. So imagine, one that I investigated was they were flying around a gravel pit up in Kansas someplace, and there's some bad activity going on in the gravel pit, so these guys wanted to see what was going on. So they flipped around, just did a right turn there, and they were so busy looking out of the airplane, they weren't paying attention to where the wind was coming from. And they spun out of control and crashed. So the Army came to Bell and said, would you investigate this? So we got to asking ourselves the question, how would you actually investigate this? So I said we need a powered model of some kind that had a main rotor, a tail rotor, a fuselage, so that we could begin to look and see what was going on with the airplane. So I need a power model to do. Anybody who's ever built a powered model knows it takes a long time to build a power model. The best we've ever done at Bell is about 18 months. Well, I didn't have 18 months. So I know everybody thinks that all this autonomous UAV stuff is brand new and never been done, but that's not true, because I brought the world's champion 206B RC model from the world champion for a few bucks. And what I did is I put it in the wind tunnel. I stuck this thing on a pole. So I went to this wind tunnel test, and we spun this thing. This is about 20 degrees per second yaw rate as you go around. I scaled the velocity to be the main rotor tip speed, so as equivalent speed. And when you see that, you can see I put the wind right on the edge of the rotor, so you can see how the tip vortex of the main rotor blade actually affects the tail rotor. So from this, we began to look and say, okay, what are the contributors? What are the real contributors to it? So we noticed from the wind tunnel, and you can see this, in the left-hand side, the main rotor tip vortex is a region where the tip vortex will actually intersect the tail rotor. So what was that wind zone? That wind zone, depending on airspeed, can vary a little bit between 315 and 280 azimuth. So think about azimuth. What does azimuth mean? Straight ahead is either 0 or 360. This is 270. If it's coming up your tail, it's 180. If it's coming off the right side, it's 90. So just think about you're sitting on a compass, and that's sort of the way you read this. And then these are speed bands in between. So basically, we found the main rotor disc protect on the right side. We had this thing called weathercock stability. If you heard of stability control, you put a vertical pin on a tail rotor or airplane for what reason? To keep it aligned to the relative wind. And that's what it does. So basically, if the wind was from the rear from 120 to 240, the airplane would want to turn around, nose into the wind, which was exactly what it was designed to actually do. Then the other issue out there is tail rotor vortex ring state. There's been tons of literature on tail rotor vortex ring state. We're going to talk about it on. And in a tail rotor, what happens is you get into a certain zone from 210 up to 330 degrees at certain speeds. Basically, when the tail rotor wake becomes behind the tail rotor itself, like here, well, then it'll begin to oscillate. And it will actually break away, and then the pilot will have to make a control input to regain control of the aircraft itself. And so what happens if you're flying aircraft, I tell you to point the aircraft right there, and from the 270 thing, the pilot will have to move his feet like this to try to hold that heading. And he won't be able to hold it very precisely, but he will be able to hold the heading. And we know all this because fundamentally we've done flight tests on this forever. Other people had looked at that. Wiesner and Sheridan at Boeing had done a lot of work. So now let's see what the results of the that were causing this phenomenon called loss of tail rotor effectiveness. So along the x-axis down here, we have where the wind is coming from. You know, 360 or zeros out the nose, 270 left side, 180 tail off your tail, 90 off your right side. So if you think about a tail rotor, we ran this test with collected, was fixed. So the only thing that was changing on the tail rotor itself is the inflow angle. Or if you're thinking about a fixed wing, what's the induced angle out the back. In our rotorcraft world, we call it inflow angle. And so basically, the upper line, the dashed blue line, is what the fuselage was contributing to without the rotors to see. So the red line represents just the tail rotor only without the main rotor. So you can see here that at a fixed collective pitch, all the way around the azimuth, the tail rotor really never stopped producing thrust. However, you can see the unsteady ring right there where the vortex ring state was, and then you can see where the aircraft got into weathercock stability. Well, you can see that the weathercock stability, the slope in the weathercock stability was steeper with the tail rotor on than the tail rotor off. So that was sort of something we'd really never thought about. So basically what happens is if you rotate into that area, you will actually accelerate quicker than just the basic fin because of the tail rotor inflow angle changing during that time. So this is okay. So we were answering the questions for the Army. Okay, so then we put the main rotor on and repeated the same test. This is at 10 knots, with a side dot, yaw rate at 20 degrees per second. An interesting thing happened here. Put the green line right here, suddenly there was a tendency, there's a more yaw moment. So left yaw moment tends to, the purpose of left yaw moment is to rest the right yaw moment, right? So the pedal is actually pushed in to do that. So if I told the pilot and he was going around that gravel pit and he wanted to have a 20 degree per second turn rate, suddenly he was slowing down. And he went, why am I slowing down with my turn rate because I'm not getting where I want to go on the flight path? So then he would push right pedal. And so he would push right pedal to try to compensate for this change in the moment right here. About that time, the main rotor tip vortex got on the other side of the tail rotor, changed the induced flow of the tail rotor, and suddenly accelerated him. And he wasn't expecting that acceleration. Then he quickly rotates through the tail rotor vortex ring state. That didn't really change. Went back into the weathercock stability and came out. So I said, okay, we got this settled. We have this solved, you know. Well, the Army said, not so quick. He says, this is a wind tunnel test and we do not understand. Was it right or was it not right? So they said, we really, really want you to go fly this in the helicopter, okay? So as we're getting ready to go flying, I can remember my boss at the time, Jan Dries. In fact, I found this note where he wrote me in my files that said, whatever you do, do not crash the helicopter. You talk about putting pressure on you, that put pressure on you, okay? So then the question was, okay, how do I do this? So basically, I went and the team went together and we put together an aircraft and an OH-58. And we fundamentally went and put a low-speed system in it so we know where the wind's from. And we instrumented it up. And anybody that's ever done flight tests knows for a helicopter, you want zero wind. Well, this is one of the few times where I had to wait around for wind. I needed a steady wind to actually do this test. So in this case, we waited around and we had a steady wind of about 16 knots, which is pretty stout from a wind. And we went out and we did a right hovering turn. Now, I got to tell you, that most pilots made fun of us. Most pilots say, this is not what's going on. You know, there was a lot of deal. So I had to talk to my pilot, who's a good friend of mine. We did a lot of testing together. I said, you have to learn to let the aircraft get away from you. In other words, you have to not be the ace pilot you think you are. You have to be a sloppy pilot and be distracted and let the airplane actually get away from you. So here we have several parameters plotted. Red is the yaw rate in degrees per second. The pedal is the purple. It's in percent, right? And the collective pitch is there as percent up. So you can see we went in there, we went and did the little test, and lo and behold, we actually accelerated up to 90 degrees per second yaw rate. And we were able to recover successfully all the way back to minus 15 degrees yaw rate. So the pilot got a little more confidence out of that. He understood he had to actually let the aircraft go. So we actually went out on the runway and we did up to 120 degrees per second yaw rate, at which time the pilot was becoming disoriented visually from spinning around. the old emergency procedure says reduce left pedal, apply forward cycle, reduce collective. The new emergency procedure, and we proved this to the Army, was apply full left pedal till you arrest the yaw rate, apply forward cyclic pitch, and as recovery is affected, then you adjust the controls for normal flight. And so basically, you know, we actually found the answer to the question. The new procedure did it. The Army wrote about it. And basically what it came down to, the Army put out a training film, was when you're doing these turns and everything, flying the airplane. Are you flying the airplane or is the wind flying the airplane? And so as a result of that, the number of incidents really went away. No one could say the tail rotor was stalling anymore. So we managed to resolve that. I'm going to move on to some performance questions that we actually had here. So Frank Harris, I invited him to come to an aero session. We had a specialist meeting at the American Helicopter Society in Arlington, and he wrote quite a epistle that he put out there. And basically, he went and took some data. And we took some data from a 40 by 80 wind tunnel test of an S-76 rotor. And you can see the thrust coefficient versus the effective induced drag. And so the question was, how well do the test points line up with what Glauert said and what, you know, Wayne Johnson ran his CAMRAD code, which had the Dr. Mike Scully's free weight in it. As you can see, the free weight was doing really good. I want to call your attention to the Glauert K factors. K factor to go a mu of 0.4 was 1.95. So I said, if you look at his time, you know, they thought that induced power went way down with forward flight. This, as induced power starts to come back up as advanced ratio goes up. And that was a significant finding, and there was a lot of obvious questions about that. So then along came Charlie Crawford. He gave us a report. Anybody that knows Charlie Crawford knows that he ran the Army evaluation for the UH-60s, for the AH, and for the OH-58D. So he gave us a report card. And what Charlie's message was in his Nikolsky lecture in 1989 was, we need to improve our analytical capability, guys. We're not doing a good job for the customers. On the upper left, we see that everybody missed hover performance by at least 5%. Another subject I'm not talking about today, I'll be happy to see a Nikolsky lecture on this, is what's the weight growth. And these comparisons are made between what you had in the proposal and what you actually flew at Edwards Air Force Base. So you can see the importance of weight. Weight was a real challenge. So you can see the best guy was just under 10%. The worst guy was north of 15%. So the problem with the customers, remember I told you at the first onset, your job is to deliver a product that can have a certain performance at the mission weight. As a result of that, when you stack this up, you can see what a challenge we had in those aircraft. None of them really met the spec that was out there, and you can see you could potentially have an error as great as 25%, which would be quite a miss. So Charlie's message was, something's wrong here, guys. We really fundamentally need to actually get our analysis up to speed so we know what the real answer is going to be ahead of time. So Bell went back, we put the Scully Wake in our copter code, which is our code that actually calculates things. And you can see here, the slide line goes through the flight test points as opposed to the dash line, which is a momentum theory using the uniform inflow. So basically, the Scully Wake affects the inflow on the aft part of the rotor, which changed the induced velocity significantly. However, there's a lot of questions about the free wake and what was actually, how good was that? Okay, so Bell was teamed with NASA, and we actually made a rotor, a model rotor, took it to the 14 by 22 with NASA. At that time, NASA was actually trying to use laser velocimetry to actually calculate velocities around the rotor. And so we teamed with it. We were going to get air loads. This was a pressure instrumented rotor, and we wanted to see how well we were measuring what the wake was doing out of that. So we made an image plane in the test, put the laser light sheet down the little dash line, and then we had predicted we could see these 1, 2, 3, 4 intersections of it, and we could capture the tip vortex. So we took this picture, we had a grid line, and we could identify where those tip vortexes actually were at this advance ratio. So the question is, okay, we could identify the tip vortex. So let's see how well we did with our predictions. So you can see between the circles is where I thought it would be. I would find a vortex. The solid dots are where I actually found a vortex. And you can see that on the back part of the rotor, we were pretty good. We could identify the core locations. However, in the front, we were very disappointed. We were way high, and at first we did not understand what was going on. So then we remembered our deal about you got to pay attention to the mounting system. We went back, ran a VS Aero model, and found out we actually, the fairing at the bottom actually made an upwash that moved up the rotor weight on the front part of the disc itself. So meanwhile, the types of rotors have been going along, and Bell had actually come up with a bearingless rotor. And so NASA wanted to test the bearingless rotor and find out, could they reduce the drag, the hub drag. As a result of that, they did this wind tunnel test. You can see here, they tried pretty much the same thing, a large fairing, even had a big cone on top. And so let's look at the results of that. You can see the hub fairing alone was actually greater than 9 square foot. They put all the fairings on, and they could reduce the drag down to about, looks like about 7 square feet. We could do something, but however, we found out when you put all these fairings on that you negatively affect the lateral direction, especially the directional static stability. And you actually end up with making it negative, as shown on the slide on the right. 1982 at Bell, we started trying to predict a fuselage using a half-span representation. As you can see, we did pretty good. We got a couple data points in red compared to the blue, and we were pretty good on the centerline pressure. However, it took about several months to run this, so in the design cycle, that was not going to actually work. So the question was, okay, how do I actually use CFD in the design thing? I established a policy where I would make them pre-predict what was going to happen in the wind tunnel. If you pre-predict, I'll put it in my lockbox, you go run the wind tunnel test, you come out, we compare, we have a conversation. They did that. They did not match the force in moments. At this time, we were using overflow, which had a structured grid, which took a very long time to actually do it. But once they got the grid correct, they matched the forces in a moment. And then I said, okay, I have a couple of problems right here. I have an angle attack up in the upper right. I have a high drag, and that high drag is separating and reducing my fin effectiveness. So tell me what I can do in CFD to fix that problem. So they did that. They came up with a different fillet at the wing root. I built that fillet, went back to the wind tunnel test, and verified it. So the lesson learned here from me was if I can get the grid right with my CFD guys, I can believe that their fixes are good. And that was a big finding and a very interesting finding, because from then on, when you have flow problems in the wind tunnel, you know, you get your clay out and you try to make it look good and all that, but you never know what it looks like. So the CFD guys can actually really help you out there. Moving on, then along came the V22, which presented a whole new set of opportunities for aerodynamicists. And anytime you change the configuration significantly from the normal, you begin to find that there's a new set of problems to look at. And that's what makes engineering interesting. There's always new challenges popping up. There was one set of data. It's the first time we ever had any hover data on a tilt rotor that was an isolated rotor itself. And so we went out there, and NASA ran this, and they have isolated and the semi-span download test as shown here. This data set has been run so many times, and people have looked at it for so long that even today we're still trying to get better correlation with that data set. So first thing we found out was we can't predict high thrust. On the left, you can show our analytical codes. They died prematurely. So we didn't understand what was going on. So then we went to CFD, and we found out a variable, something that's very different. We found out that in a fixed wing, the boundary layer stays stuck to the wing doesn't rotate, the flows goes up over the boundary layer, right? In a rotating system, the boundary layer experiences a centrifugal pumping, and that centrifugal pumping energizes the boundary layer, and the boundary layer actually stayed attached. So what you see right here is a real high angle of attack at the fat end of the rotor blade, and you can see how the flow vectors are still attached. And what this really did was we had the results here from the lifting line, the CL as a function of the rotor radius. The red line is what the lifting surface would say using the 2D airfoil tables, and the CFD showed a really high CL max in there. And we corrected that. We began to get better correlation with it, but that took a long time to run that CFD model. So the question was, how could you actually put that in your blade element analysis, which uses 2D airfoil data? So we went to work on that. So we figured out a methodology to put stall delay into the program. And what stall delay did, we would extend the 2D airfoil tables, and John Corrigan found some work done by Banks and Gadd, who had found this out from some propellers that they had run. And so we came out with a process to do this empirical stall delay. We put it in there. This is a V22 model, aeroelastic model, about 60 knots at 60 degrees nacelle. And you can see how much improvement there was between test and the data. So then another area that we were always interested in was hover down load. So basically you hover down load, you have a rotor pushing force down on the fuselage. So the question was what we could do. So we actually went back and repeated small scale the ORF data. And when we did that, we found out we could agree with what they had measured on ORF. So we went to work to find out, okay, what can I really do to actually make the flow do something different? So we had two configurations. We had a configuration one, we had a flow diverter, where we tried to make the flow go this way. We put a prism back there trying to help the flap. We put a fence on the front. And then we went really wild, we made this giant prism. So the question was, okay, what happens there? So here we went to this guy, and we actually built this thing and actually went to test. So this is configuration 1 on the top, configuration 2 on the bottom. So what we found, you can see the solid is what we got out of flight test, small scale dash, and you can see that we actually got better stuff. But then when I'm briefing this, I'm all asking myself, this looks pretty stupid. Why did I really take this to flight test? So it really takes a lot of courage sometimes to go experiment in flight tests with strange looking stuff. So then Meakin, in this time frame, went and actually ran a rotor. And he actually found that he could try to simulate this. Now remember, there's an image plane on the left, the free edge of the rotor's on the right, just like from the ORF test. This thing ran months. Okay, so Bell, meanwhile, we went and we tried to measure the flow using a triaxial probe. But what we found out was we knew the angularity of the probe, so we took very small steps underneath the rotor, and we made sure that we were always in alignment from step to step to step to try to get some good measurements for the actual probe itself. And this is the results of that. This is the time variance on the right. We're going to calculate the vorticity field. You can see the vortex. You can see some of the sheet actually falling down in that. So the question was, how did that really compare with the CFD? So we went and took the measure of the black lines. We took the Meakin data. We had fair correlation. Pretty darn good. We could get the edge of the wave. We could get the recirculation around the bottom of the thing itself. So then the question then was, okay, what does that really tell me? However, at that time, Professor George at Cornell and Polak had come up with this deal and said that the structure from acoustic point is not the same. The image plane doesn't really handle the vortex correctly. So on the far left, you can see the vortex recirculates. The one in the middle shows that it goes from side to side. The rotator, because there are two rotors both dropping off, and they go back and forth. And we had actually observed that in flight test on the XB-15. In the far right, we see that from a performance point of view, it's had very little effect because the mean induced flow was not changed any. So from the performance point of view, it seemed to be a problem. From the acoustics point of view, the vortex interaction, of course, is the big driver in acoustics. So that made the difference. So then Strong and his team out at Ames, they began to calculate this using overflow. And they actually came in and had the half-span model and the full-span model that basically repeated, if you will, what they had seen from George and Polak in that area. So things are looking up in the CFD world. There's still some issues there that we're still trying to work. But meanwhile, we wanted to see, okay, what about active flow control? You know, what's going on in active flow control? So I was working with Professor Wojnowski out at NASA, at University of Arizona. He did 2D simulations, and he found this is called zero mass blowing. And basically, you put momentum in at a certain frequency and magnitude, you take momentum out of the trailing edge there, and he could actually affect the vortex structure underneath the wing itself with this. So it was encouraging enough, so DARPA gave us all a little money, and then we were able to actually then go run and see what would really happen. They made actuators like speakers. Remember a speaker like this? They made these actuators. We actually put it in there. And so the way it worked was you would push air out, you'd suck air in. You push air out, you suck air in. And you do that at a certain frequency and a certain amplitude, and then it would attach the flow. So actually we were able to get a magnitude of this case, and we actually calibrated it before we went out there. So we were getting about 85 meters per second with a, at a frequency of about 50 hertz. So you had to work in the frequency that would actually affect the boundary layer itself. So we actually went and tested it, and we actually got about 150 pounds improved lift. And I'll show you how the flow was actually attached to the wing. So here it's off. You can see the tufts outboard are going up on both sides of the aircraft itself. The minute we turn active flow, and you see the tufts are attached. So this is the first test of a active flow on a helicopter that we were aware of, and Wiggie's very proud of that. And we had a lot of fun doing that particular test. It was only fitting that the XV-15 took its final resting place in the Smithsonian up there next to the Concorde. And we thought it was pretty fitting that the last flight of the XV-15, even though it did many experiments during its time, was really on active flow control. Next, we want to talk about vortex ring state as it relates to the V-22. This picture was taken by my boss in 1951. And you can see here the flow breaks up and then it breaks out. And that's a repeating flow in the wind tunnel. And the reason is that that's a fixed, the wind tunnel cannot actually leave. So a guy named Newman, he extended momentum theory where you can see the black line and the purple line, and then the red line was what we actually measured on the V-22. So next, Wayne Johnson went and did a lot of work. He actually characterized all of the VRS tests, of which there were many. And we found out a very interesting thing. There's a certain climb ratio, which is your sink rate over your induced velocity, where it has positive damping. In other words, I put up collective, I'm going to get the right response or plane of climb. We found that there was a negative thing, where it's a negative damping. No matter if I pulled up, I would still keep falling. So that was an interesting finding as we go through there. Because remember, there's a singularity in solving the induced velocity in momentum theory that causes a challenge for you there. So in the green zone, where it's positively damping, when I pull up, my induced angle is corrected and I actually get more thrust. So it doesn't hurt me there. However, if I have my sink rate really fast, right here, what happens is negative damping. No matter what I do, then the wake that's getting close to the bottom of the rotor will actually wash out any collective pitch. And you just keep sinking faster and faster. So this is sort of a simple explanation of what really happens. The next thing I want to show you, on the left, there's our model. Mark Dreyer actually went and modeled all these vortexes and show how it gets up underneath the rotor and how it will actually break away here in a minute. And then boom. And when it booms like that, if you like the dancing red dot, the red dot then falls down to a more stable position. So there's a couple things to know, right, that we found out in flight tests. We had to go through a lot of trouble and flight to do it. But there's one thing we learned. Rings do not maneuver. You can maneuver away from the ring. The ring will not follow you in maneuver flight. And so with that, obviously you go fly and then you can maneuver safely by just simply changing your flow state and maneuver away from the rings. CFD marches on. We got unstructured ships. Things got a lot better in CFD because of that, because your meshing can go a lot quicker. And we began to look at the hub again. So here there was a big effort by the VLC to go do a hub test and do it. This is a hub test, a comparison between the green and the red. And so the CFD was really beginning to look good. Dr. Chen at University of Toledo, he has really been working a lot on this. And you can see we really have a problem in comparing with the measured data with the tip out there. And the real question is, look at that tip stall. And we actually had tip stall, and he's been trying to work very diligently to try to do a different treatment in the CFD out in the tip. So if anyone here wants to fix that problem for me, I would definitely appreciate it. So then we moved to our latest helicopter, which is the 525. And we used this CFD extensively. We went to the wind tunnel. You know, the drag looks really good. Not perfect yet, but very usable. So based on that, we were able to do a lot of design changes during the actual design of the 525 aircraft based on a single wind tunnel entry into the program. So let's see how I'm doing on the 525. I'm doing okay in forward flight on the 525 today. So I'm going to give you my perspective. At the end of the day, guess what? Analytical capability has really made significant improvements over the years. However, I don't think you're quite to the level of the fixed wing, so there's still work to be done there. Rotorcraft will always have uncertainty that will always require flight testing. Wind tunnel tests for fuselage characteristics is not extinct yet. But however, to positive for the CFD, it can really guide the design today. And then finally, emerging new configurations such as Lightning Strike will have its own challenges and opportunities for all you young engineers to work. Thank you very much.
There's a lot that goes into testing in environments that are similar to a launch environment. When you have such a violent launch on top of millions of pounds of thrust, ridiculous vibrations, so we actually have a vibration table in the Space Physics Research Laboratory that allows us to shake the